Hi there. This video is a continuation of our discussion on Maxwell-Boltzmann distributions. We've already seen one pertaining to our molecular velocities, so the different x, y, z components of the speed of our molecules. This video is going to focus on how things get modified a little bit if we want to focus exclusively on the molecular speeds. Okay, so rather than just considering one component of our velocity like last time where we took the x component and focused on that, here we want the overall speed, or we want to describe the overall speed. Okay, so this is again not going to be a vector. It's not going to specify a direction for us, right? So our new function is going to look like this, where we have a product of all of the various components of our molecular velocities that make up the speed. Okay, so the only thing that's kind of new here from last time is that we have this added du here, so we have fu du, whereas before I think we just had an f of u of x. Before, all this notation does is to tell us that we're calculating a probability that the molecule is going to have a speed somewhere between u and u plus du. Okay, so we can use this function, we'll see in a little bit, to help us do some calculations for things like average values and to normalize the function and things like that. So really just when you see this form of your function times du or dx or whatever your variable is, it's giving you a probability. Okay, so all we're really doing here is we're going to substitute the equation, the velocity distribution we used last time that we saw for f of u of x. Okay, remember there's going to be similar ones for the y and the z components as well. So we're just going to plug those into this expression, and then remember that we can put everything in terms of just our molecular speed with this relation here. Okay, again, McQuarrie and Simon has a section where it goes through where this relation comes from, but just remember your overall speed is a combination of all of the different directional components. Okay, so just kind of going from that velocity space to our speed space, if you will. Okay, and then we also need to account for the fact that we're now looking at kind of a three-dimensional velocity space rather than a one-dimensional one that we did previously when we were looking at just one component of the speed with that x component of the velocity. So that just gives us a couple of other things to factor in. Okay, so when we plug all of those things in, again, the book goes through all the details of that. So if you're interested in the details of that derivation, just check out McQuarrie and Simon. But we end up with this lovely expression for our Maxwell-Boltzmann distribution of molecular speeds. Okay, so it looks very similar to what we had previously for the velocities. Okay, there are a couple of differences that I'll point out in a second. Okay, so let's take a closer look at our new expression. Okay, the main things that are different from the expression we had before for the velocities are this 4 pi term right there. Our exponent is to the 3/2 instead of the 1/2, and we have this u squared term that pops up in there. Okay, so again, that the 3/2 instead of the 1/2 is just a factor of the fact that we're taking all three of our components, the x, y, and z, okay, together. So if we remember back over here, we have a product of all three of those dimensions. Okay, so we're getting a cubed factor in that exponent now. And then the 4 pi u squared. Oh, and we get an extra du here. Okay. That part is coming from, again, I mentioned that we're taking into account that we're now going to be looking at a three-dimensional velocity space. Okay, so we're kind of switching into what we call spherical coordinates, which you may remember from a math class. But we're basically just factoring in our new volume element, which is a spherical shell. Okay, and so we get that 4 pi u squared du that factors in as our volume element now, and then that gives us our new expression for looking at a distribution of molecular speeds rather than velocities. Okay, so again, I like to plot these things and get a picture of what this function is telling me. Here is a plot of the distribution of molecular speeds for a sample of nitrogen at 2 different temperatures. Okay, probably looks pretty similar to what you remember from our plot of the velocity distribution in the previous video, except there is a ever so subtle difference between the two. A couple of differences, actually, that we want to point out. One is notice that these functions are not totally symmetrical. Remember, our velocity distribution was totally symmetrical about 0. Right? We essentially had that Gaussian distribution or bell curve. Okay? These tail off a little bit, you'll notice. It's a little subtle to see, but that tail at the higher speeds, right, kind of is elongated out. So these are not totally symmetrical functions. Number one. The other thing that you'll notice is that our x-axis, right, is a little bit different. So the velocities were centered around 0 and could take on both negative and positive values, right? Because if you have a velocity, a vector, it can go positive or negative direction. Okay, speeds, molecular speeds, can only be positive, right? So if you think about your car, your speedometer, you can't go negative miles per hour, right? Same idea here. Okay, so our x-axis is only going to be positive values, so we start at 0 over here. Our functions are no longer centered at 0, but they're centered at some value. Okay, so those are just a few of the distinctions between when we're talking about molecular speeds, which we are in this case, versus molecular velocities like we were talking about in the other video.